Hello, and welcome back to a video series on MAC 1140 Precalculus Algebra. My name is Sean Perry. These are guided notes number 12 in the series on section 2.7, exponential models. There are many real-world phenomena which are modeled using exponential functions. Some of the most common include population growth and radioactive decay, as well as compound interest, which is one of the original ways that we discovered and started using the exponential functions and the natural base e in particular. There are also more advanced models and applications, such as drag forces, thermodynamic equilibrium, and logistical growth, which is sort of like population growth if there was some kind of maximum carrying capacity. Eventually, populations experiencing exponential growth will run out of food, so to speak, and wind up with a maximum possible population. And we could also use exponential functions to model these. One of the reasons that exponential functions appear in such a wide variety of phenomena is that they can appear when quantities that change over time change at a rate which is proportional to the size of that quantity. If there are more bacteria to replicate, then we anticipate the rate of replication of those bacteria to also increase. The faster I move through air or water, the greater the drag forces that try to restrain that. And the more different the temperature of an object from the temperature of the background that it is embedded in, the faster the rate at which it will approach that background temperature. The most common models using exponential functions are those modeling growth and decay, and these are the ones we're going to take the longest look at. These are ones where some amount of stuff is given by the initial amount of stuff multiplied by some kind of proportionality constant, which is given by e to the power of some constant affecting the rate multiplied by some unit of time. Depending on the sign of r, this will affect the behavior of this proportionality constant, which in turn affects the amount of stuff that we have. So to recap, a will be the amount or value of something at a given time t. P will be the initial amount, and that should be kind of clear because if we set time equal to 0, then e to the rt would be e to the 0, which is 1, and then a will just be equal to p times 1. So we would just have that the amount of stuff we have is this value p at time 0. The reason we see e in most of these formula instead of some other base is because e to the x has fairly special properties which are related to rates of change, and a discussion of those might take us a little outside the scope of the course. Suffice to say that you kind of have to wait till calculus to see why e would be called the natural logarithm. R, which is sometimes called by k or other letters, is our growth constant. It's going to be determined by the specific problem, and the units of r are going to be 1 over the units of time. That way, RT cancels to a dimensionless unit, and when we raise e to the power of that, we just get this dimensionless scaling factor, which doesn't change the dimensions of p and makes everything kind of work out nicely. If r is a positive value, then the model will give us exponential growth. It's a misconception to think that exponential growth begins at this kind of hockey stick part of the curve. Exponential growth is something that's happening all along in this model, regardless of where we look. And it's really just a matter of scale when this apparent takeoff starts to occur. But suffice it to say that a hallmark of exponential growth is having this sort of increasing rate that gets faster and faster as we get larger and larger. Exponential decay, on the other hand, is the reflection of this over the y-axis, and it has to do when something happens less and less frequently or with slower and slower rate as less and less of the stuff is present. One of the main phenomenon that refers to this is the decay of radioactive elements and isotopes. One of the reasons it's called exponential decay. So time will be given, measured in some unit. That will again depend on the problem, whether or not we're talking about hours or minutes or years. It really depends on the context. And these two r and t go hand in hand. A different r would be required if we were to change the units of t. Likewise, if r is given and we want to fix it, we have to make sure all the units of time that we're working with are given in the same unit. And I just want to say one more thing about the anatomy of this model, which is that this part, e to the rt, we really can see it pretty easily as being this proportionality factor, right? It's going to be a dimensionless constant that's going to tell us how a and p are related to each other, by what factor. And you can see that by dividing p over to the other side. And then you see that the ratio of a to p, the ratio of the amount of stuff we have versus the original quantity, is equal to e to the rt. So that's what e to the rt is telling us. It's telling us the proportion of a relative to p. So let's jump into the guided notes. Here they are asking us about a bacterial culture who is modeled by this equation here, where n of t, n as a function of t, is the number of bacteria in the culture, and this is equal to some constant times e to the power of some other constant times t. And the first thing they're going to want us to do is sort of break this down in terms of what these two numerical parameters mean. The rate of growth, or growth rate, is given by this value here. As a percent, 0.1 would be given as 10%. The initial population is going to be the value of n when t is 0. And you can see just by setting t equal to 0 here, it would strike this part to 1, and we would just get this leading coefficient, 970. So the bacterial culture begins with 970 bacteria. How many bacteria will the culture contain at time t equals 5? So now we're being asked to figure out what is n of t, given some particular value for t. In other words, what is n of 5? So for these kinds of computational problems, and in fact for much of this chapter, we're going to rely pretty heavily on our calculators, although I encourage you to consider for a moment how tricky it would be to figure this out, even to some small number of decimal places, in doing this by hand, where e could be taken to some decimal approximation beforehand and worked with in terms of just raw arithmetic. But we're not going to do that. We're going to use the calculator. Plug in 970 times e to the power of 0.1 times 5, and we get 1599.2. It wants us to round to the nearest bacteria, and so that's going to mean rounding to the nearest whole number. And that gives us 1599, or 1599 bacteria after 5 hours. Here we have a slightly more difficult question, as this one requires us to solve for a variable which is inside of the exponent. But that's what we spent this chapter learning how to do. They tell me that at a certain time, my population will exceed 4,607. If we plug this into the model, we see that the only thing we're really missing is time, which is what they're asking us to solve for. To do that, we first want to isolate the exponential part by dividing 1450 to the other side. That frees up the exponent, and we can now solve for t just by dividing by 0.17. So we can plug that all into the calculator as such, and we get 6.800 and so on. Rounded to one decimal, this is of course 6.8. And specifically, since they tell us that time is measured in hours, this is 6.8 hours. Number 3 says a fox population has a growth rate of 1.5% per year. It is estimated that the population in the year 2024 was 9,400. 2024 is going to be our year 0. Our growth rate is going to be 0.015, 1.5% written as a decimal. And in this year 0, we have an initial population, p, of 9,400. Combining these two parameters together, we have that a is equal to 9,400 times e to the power of 0.015t. Now in 2032, the value of t is going to be 8. So we want to plug this in for our value of t and evaluate. A, or the population of foxes at that time, is given by 9,400 times e to the power of 0.015 times 8. And plugging all that in, we get 10,598.47, and so on. Rounding this to the nearest whole number, because we're talking about foxes here, which are measured in whole numbers, we get 10,598. Compounding refers to how often we reassess what value we should be applying a certain percentage of interest to. Say, for example, we wanted to reassess how much was in a bank account every year and then apply some new amount of interest to that. This would be annual compounding. If we instead gave only a fraction of the prescribed percentage, but we did it more often per year, we would have to look at the amount that that principal value had increased before we applied how much percentage of interest we should be adding back into the account. So this is again an example of something where the more that we have in the account, the more interest we would want to add. But it's quite interesting because they're adding a fraction of the percentage of the interest to the account. We're adding less and less each time. We're just doing it more and more frequently. And it was precisely considering this model with r and t both equal to 1 and letting n go to infinity that E was first discovered. When this particular model was investigated, as n goes to infinity, it was found to converge to a particular value which we now know is a fundamental constant of mathematics. It is an interesting exercise in variable substitution to show that when we let n go to infinity, our model becomes the familiar exponential growth model we've been looking at. Problem 4 asks us to investigate a situation with r equal to 0.02 and p equal to 4,000. This would be modeled by 4,000 times e to the 0.02 times t. How much will we have in 10 years? Asks part B. Well, then a of 10 would be given by 4,000 times e to the 0.02 times 10. We're not asked to solve anything here. We're just asked to evaluate this expression, which we can do in this fashion. They ask us to round to the nearest dollar, so we would have 48856 and so on, which would be rounded to 4886. Problem 5 asks us about another population growth problem. Here, we're actually asked to find the continuous growth rate r. What we're going to need to do is establish a time 0. Let's take that to be 1980. And then in 1990, this would tell us a population at time 10. The value at time 0 will be my p, and this value here is actually a of 10. So let's use those to solve for r. If 515,761 is what we get when we plug in 10 into the following model, we now have enough information to solve for r, the growth rate. Dividing 493,846 over to the other side, we isolate our exponential, and taking the log of both sides, we free up the exponent. All that's left to do is divide by 10, which gives us an exact value for r, and plugging that all into our calculator, we get the following, which we could round to 4 decimal places as such. Problem 6 is going to get us into the idea of radioactive decay and carbon dating. It says that a skeleton was found under a parking lot in England that was thought to be the skeleton of King Richard III. Suppose a sample was taken and was found to contain 90.99% of carbon-14 it would have initially had. Carbon comes in several isotopic varieties, and the varieties that are produced geologically have different ratios of carbon-14 and 13 than are produced biologically. We can use this change in ratios and the decay of carbon-14, which happens at a known rate, in order to determine the age of biological material and how long it has been since that material was alive. One of the main features of this problem is the idea of half-life. Half-life is the time such that the ratio a over p is equal to 1/2. And if we look at how that relates to growth rate, we find this expression. So the first thing we're going to want to do is take this information about half-life and calculate the growth rate. Then we're going to want to take the proportion of a to p that we're given and calculate time based on that. So let's begin by calculating the growth rate. This calculation will be the same for any half-life problem. We know the ratio of a to p will be equal to 1/2 when we have e to the r times 5,730. So the ln of 1/2 would be equal to r times 5,730, or Dividing my 5,730 over to the other side, we have the growth constant for r. This gives me a value of negative 0.0001209,680, and so on, which I will take to be approximately equal to 0.000120968. It's good to take a few too many decimals rather than too few when we're doing an approximation in the middle of our problem, because I'm not asked about the growth rate. I've been asked to date this proposed skeleton of King Richard III. So now we want to work with the given ratio of the amount of carbon-14 versus how much it would have had originally, which was 90.99% or 0.9099. And we're asked now to find at what time that would have been the ratio given the decay rate of carbon. So we plug all of what we found in. We have now negative 0.000120968 times t in here. Taking the ln of both sides and dividing by this growth rate constant, we could get t. And what we get is 780.5 years, which we could round to approximately 781. Now, I don't know very much about English history, so I'd have to look it up. But King Richard III apparently died in 1485. So it appears our skeleton is about 250 years too old to be King Richard III. Problem 7 gives us a question about how much radium, which is a radioactive material, will remain after a certain number of years. We're told its half-life, and so the first thing we should do is determine its decay constant. We can do this by solving the equation using the proportion here. Again, half-life is the time at which the ratio of the amount of stuff to the amount of stuff originally is 1 to 2. And so we'll be taking the ln of 1/2 and dividing by 1590 to get r. If you're using a TI calculator or similar, a nice way that you can avoid having to do all of those decimal places to keep your answer accurate is to simply store the value in your calculator as a certain variable. Here I have a button called store, and if I put that in as some letter, let's say r for consistency, it will remember this decimal value. And that way, when I go to do some kind of evaluation using r, I don't have to type in all of these decimal places. I can just type in r. Now, they tell us that the initial sample contained 500 milligrams, and we now want to know how many milligrams will be present after 2,000 years. Well, that'll be 500 milligrams times the proportionality constant given by e to the r times 2,000. Since we actually know r, I'm not going to solve for anything here. I want to know what is this amount. All I have to do is plug this into the calculator. And now that I've stored r as this variable r, I can just use that letter when I type this into the calculator, and it will do the most accurate job we can do. So here is my r times 2,000, and we are given that 209.08 and so on will remain. Let's round this to the whole number of milligrams to say that 209 milligrams of radium will remain. In this question, we're asked similarly about some mysterious radioactive substance. It says that the scientist begins with 100 milligrams, so we know P is equal to 100, and they say after 15 hours, 65 milligrams remains. So we know actually A of 15 will be equal to 65. We want to figure out the other constant, the R constant from this, so that we can then answer the question, how many milligrams will remain accurate to at least one decimal place after 26 hours? So this is our question now. What is A of 26? And to do that, we're going to have to answer the question, what is R? So we begin by saying that if 65 is what the model gives us at time 15, solving this for R by dividing 100 over, taking the ln of that, and then dividing off our 15, we wind up with the following expression for R, which I am going to store into my calculator as R, so that I don't have to keep recalling it to some decimal approximation. I just have this as my R. But for our notes, that's about negative 0.0287. And we are asking about what is A of 26. Well, so A of 26, the amount of stuff after 26 hours is going to be 100 times e to this particular r, times 26, which now we could plug into our calculator as 100 times e, we've stored our constant as r, times 26. And this gives me 47.39, and so on, which is approximately 47.4 milligrams. To find the half-life of the substance, what we want to do is solve for t, given all of these values for r and p, that gives me half of the amount of stuff. So this is a over p equal to 1/2 equal to e to the r. But now r is known, so taking the ln of both sides and then dividing by r, we now solve for time. This time is going to be my half-life. You could take this as a formula for half-life if you like. And r we have stored in our calculator, so let's just plug all that in. We have the ln of 1/2 divided by our growth constant, and we get 24.13 and so on. Accurate to one decimal place, that's approximately 24.1. The units given are in hours, and so this will be hours. The next problems deal with a different kind of model, which is related to something called Newton's law of cooling. Newton's law of cooling tells us how an object, when placed in an environment, will change its temperature to match the environment's. There are some assumptions inherent in the model. For example, that the environment is so big that it won't change its temperature because of the object heating it up, but we'll just skip over all that and get right into the model. It tells us that the temperature of the object is going to be given by the temperature of the environment plus this modifying amount, which is going to be the difference between the initial temperature of the object and the temperature of the environment times some exponential factor. K here will be a constant, which depends on the object and its rate of cooling. Now, I've noticed after having created this that they have randomly populated the temperature here as 250 degrees Fahrenheit, a truly ludicrously large temperature for your tea to be, because tea would boil at 212 degrees Fahrenheit. We're going to presume that you're either some kind of alien drinking some non-water type tea, or maybe, I don't know, you're in a hyper-pressurized room that's keeping the tea from boiling. But in any case, we're going to assume that the tea really does start at 250 degrees, even though that is a ludicrous assumption to make for any normal room and any normal tea. It says we measure the temperature 6 minutes later and find the tea to have gone down by 25 degrees. If the temperature at your house is set to 73 degrees, which is a reasonable temperature, what is the value of K? And then it says the optimal temperature for tea is 180 degrees. How long will it take the tea to reach that temperature? So the first thing we want to do is plug our knowns in and solve for K. We're told that at 6 minutes, the temperature has gone down to 225 degrees. The temperature of the room is 73 degrees. The initial difference was between 250 degrees and 73 degrees, times e to the power of k times 6 minutes. Subtracting 73 over and then dividing by this term, we would wind up isolating the exponential, and so taking the natural logarithm of that and dividing by 6, we would wind up with k. Plugging that all into the calculator, we wind up with this, negative 0.025378, and so on. And so to 5 decimal places, we have that k is approximately equal to negative 0.02538. Now, how long will it take our t to reach 180 degrees? We just need to solve this now for t, given that the temperature is 180. I'm going to take this value and store it in my calculator as k. That way I don't have to do any rounding. Solving this equation would mean subtracting 73, then dividing by this term, multiplying my exponent, then taking a logarithm to bring out the exponent, and dividing by k, which we just found. This would give me t. It's perfectly fine to evaluate these differences before you plug them in. If you're going to plug it in as I have, make sure you use plenty of parentheses. And dividing by k here, we have 19.83 and so on, which is approximately 19.8 minutes. Here we have another Newton's law of cooling problem. It says a bar begins at 1100 degrees Fahrenheit and it's quenched in oil at 350 degrees. After 2 minutes, the temperature of the iron has dropped to 750 degrees. So using this information, we will find K, then we can tell the temperature of the iron after 10 minutes, and solve for how long it will take it to reach 400 degrees. Let's write Newton's law of cooling down for reference and plug in our initial values. We now want to solve for k, which means minusing the 350 over to the other side, dividing this by 1100 minus 350, taking the ln of both sides to liberate my exponent, and dividing by 2 to finally solve for k. This gives us the following value, which I'm going to store into my calculator as k. If they ask for k to the nearest thousandth, we have that k is approximately equal to negative 0.314. What temperature will the bar be after 10 minutes? Well, now that we have k, this is just asking what is u of 10. K is now a known, so I can just type this into my calculator. Using k stored in this fashion means I have to round minimally. This gives me 382 degrees rounded to the nearest whole degree. Finally, we're asked how long it takes the iron to reach 400 degrees. Now we're going to be solving for t with, again, k known, so we would minus 350. We would divide off the 1100 minus 350 term. We would take the ln of both sides to liberate the exponent, and then divide by k in order to solve for t. This gives us approximately 8.6 minutes. This last problem gives us a so-called logistic type model, where we have actually a quotient with an exponential in the bottom. This will give us a limiting value towards which the function eventually tends. A certain community consists of 2,700 people, and one individual has a contagious strain of influenza. How many people will have contracted the flu after t days is modeled by this particular equation. Here I'm just asked for what is the value p of 9. This just means taking and plugging in 9 into my equation. All we have to do is be careful when we're plugging this in the calculator to make sure the denominator is in parentheses and that all of our exponents are in the right spot. So I would put a parenthesis around this denominator and make sure that the entire value, negative 0.35 times 9, is all inside of this exponent. Depending on the version of your calculator, your denominators may also get pretty printed in the same way, so that you don't have to worry about the parentheses. In the same way, if you have an older calculator, you may have to worry about putting in another set of parentheses around this exponent. This gives me a value of 23.1. If we round this to the nearest whole number, that's approximately 23. Here they're asking us for a carrying capacity of the model, and without knowing much about this terminology, we might be a little stumped at this point. But what we could do is graph this model and see what we get. Or we could think to ourselves about what happens as t goes towards infinity. As t goes towards infinity, e to the minus 0.35t is going to go towards 0. This we could tell just from the behavior of usual exponential decay. And if that's true, then 1 plus 2699 times e to the minus 0.35t. Well, if this part goes towards 0, then so does 2600 times that. And then this overall is going to go towards 1, because we're still going to add 1 to that. And so what is my model overall trending towards? It's trending towards 2700. This is the maximum number of people who could be carrying influenza. And of course that makes sense, because that's the number of people in the community. We couldn't really get more than that. Now it asks us how many days would it take for 675 people to contract the flu. So now what we want to do is take 675 and evaluate this model. We have 2700 times 1 plus 2699e to the power of negative 0.35 times t. And we're trying to solve this equation for t. The main idea is, as usual with fractions, we want to clear denominators. So this is going to be 675 times 1 plus 2699e to the negative 0.35t, and that's equal to 2700. Let's divide off 675 here, and then subtracting 1, and then dividing by 2699. We could now take the log of both sides, which frees up my exponent, and leaves me free to divide by negative 0.35. So all I would do is plug that whole mess into the calculator, making sure that I put plenty of parentheses in there so that I divide everything appropriately, which gives me 19.434, and so on. Rounded to the nearest whole number, that's approximately 19 days. All right, that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.